Wait, has it started, Zoe?
Yes.
Okay. Hi everyone. My name is Faiz,
My name is Zoe.
and we will be presenting our topic. We'll be presenting the topic of smart grid communication. Uh, there you go. So to start off, we're gonna cover a short table of contents. So we're gonna be addressing the current challenges of the grid in terms of communication. Then we'll go into the smart grid communication versus the classic power grid. Talk about how the system can be improved, and we'll talk about some basic smart grid communication infrastructure, uh, ways to improve the grid, solutions and technologies. Then we'll go into some active companies that implement those solutions and technologies. And we'll end with general talking about the cybersecurity risk, the goal of the modern grid, and benefits of the smart grid. So overall, this is just a high-level view of what the research nowadays is attempting to research or is attempting to figure out for smart grid communication. For all smart grid equipment, whether it be a recloser or a transformer or feeder lines. It could be anything, CTs or current transformers or potential transformers, whatever it may be. All the research is focusing on how to make equipment smart. So for example, with inverters, we covered a presentation earlier, which was talking about smart inverters. So that would be an attempt to make equipment smart. And that includes a lot of different, there's a lot of different techniques to make things smart. So that could be either in measurements or remote control or communication. The one that we're going to be focusing on, it has to do with the communication system itself, so that the smart device can communicate with what it needs to communicate with. And that also includes the algorithm that is in charge of determining what is communicating with what and what information is going where. Because ultimately, we will have, once we implement a lot of smart technology, we will have a lot of information, and we will need to figure out the best methodology to uh, share that information with these stakeholders so that we can make the system more optimal and efficient. So we're going to be focusing on the highway for communication, or the broadband communication, the internet communication, or network communication. And the last piece of research nowadays, or re, excuse me, uh, the last piece of research has to do with security, because once you have all this remote control and remote access to this equipment that affects affects everyone and affects people nationwide, you want to make sure that it's safe and secure.
So according to this image, which shows the difference between smart grid and a traditional grid from each layer of the communication, including production, market, transmission, distribution, and consumer. The smart grid can take advantages of the renewable energy, whereas the traditional grid can only use the existing large power plants. And the existing grid is one-directional centralized generation and have a few sensors, which cause a lot of unnecessary waste of time and money when there is any fault occurs. The old grid only gives out power to meet the demand but cannot receive any feedback or measurements from the receiver, so the customer is very passive. However, the smart grid has an improvement with regard to each aspect of the communication process. The smart grid has two-way integration that can sense the electric power and can adjust accordingly based on the demand, which achieve optimal operation to save energy. The sensor and smart meters can collect the data from the remote location and communicate it to the control center through a wired or wireless media. The customers will also gain more control and access to the system. Our ultimate goal is to provide utilities with pervasive measurement and control over their assets and services to make electricity delivery more efficient. The smart grid communication infrastructure consists of three parts: HAN, LAN, and WAN. HAN is home area network. It deployed and operated within a small area, usually a house or a small office. The neighborhood area network is deployed and operated within area of hundreds meters, which is few urban buildings. And the WAN is wide area network. It is deployed and operated within vast area of tens of kilometers, and it consists of several NAS and LDCs. So I want to talk about the wireless sensor network with information communication technology. In the wireless sensor network system, the intelligent sensors are placed on power transmission lines. The sensor include multiple induction coils equipped with a backup function and a chargeable battery which can work a long time. The sensing circuit allows the sensor to monitor power transmission lines in real time. The system is equipped with an infrared temperature sensor, a 3-axis accelerator, a temperature sensor, a humidity sensor, and an illumination sensor. Through those sensors, the system can monitor the conductor temperature of the power lines. And after the intelligent sensor conducts a sensing task, it transmits the sensing data to a gateway installed on the tower. The wireless sensor network is one of the wireless solutions for the smart grid communication. It also shown as a key communication technology for the control and monitoring applications in smart grids. It has a lot of intrinsic characters like low cost, wide coverage, and it's easy to install. For transmission line monitoring, research shows that the new network model called reconfigurable network model is able to handle the emergency in smart grid. It has sensor nodes that can optionally communicate with the other nodes using WANs, such as cellular networks. It can also collaborate with other relay nodes to turn on one of the WAN devices in between during emergency to balance the cost and delay. WSNs can also use for voltage quality monitor by using a cluster of sensor networks, where each one of those WSNs monitors a specific electrical grid section. It also allows power system operators to obtain system voltage quality index for each grid section by querying any nodes in the corresponding sensor network without having a central control center.
Okay, so the next technology we want to talk about are FNETs, which stand for frequency networks, or more specifically, wide area frequency monitoring networks. These consist of PMUs or phasor measurement units, also known as FDRs, frequency disturbance recorders, that are in charge of or that are designed to measure the magnitude and phase angle of voltage and also measure frequency of a voltage source. This also has the capability to communicate. So as you can see on the diagram on the right hand side, there are FDRs or measurement units at each of the important nodes of a power system. So you can see that at bulk generation, there's an FDR at the transformer to step it up high, or the substation transformer that connects generation to transmission. You have another one. You have one at the distribution sub, and you have one at the transmission sub. So all of these are recording the phasor measurement units of the feeders and the lines and generation. So wherever they are, they're recording the voltage source magnitude, phase, and the frequency of the system. Now, all of that is being kind of joined at a center or at a spectrum manager, and that data can be received at a central node. So you can see that there's a manager in the middle that's collecting all the data. So they have the ability not only to measure but also to communicate with a central node, and then that central node can pass on the data to wherever it needs to be. So in this case, or in the paper that we were looking at, they would pass on the data to a grid to a data center or a grid control center. And from there, they would analyze the data and then make improvements on the system based on the uh, real-time measurements of the system. The next technology we wanted that we looked into was smart power communication using power line consumption. So smart power consumption has to do with learning about how learning about the load behavior so that you can improve the power transfer to the system. So in this case, they use something called PLCs or power line communication, um, which allows data communication between the utility and the user. This is accomplished by using something called a smart socket. So ultimately, at the load, in this case, we're looking at a residential load in I think a province in China, where they implement this at certain houses using smart sockets. These sockets can actually measure how much loading is being done at that socket and communicate it to a local modem, which would communicate it to a local control center, and they can make adjustments, at the utility side to better meet that demand. And the system can learn, right? So once you understand what the loading is at certain times over a long amount of time, and you have that data, you can slowly adjust the power consumption and understand the power needs of the system better, and then optimize your generation and your transmission and distribution so that you can meet the demand at a more efficient to a more efficient degree. This specific study didn't study the use of smart power consumption, but the communication, the more of the communication aspect. So they looked into how effective broadband communication technology is. And the ultimate conclusion was that it's broadband communication. It has strong anti-interference characteristics that make this smart power consumption more efficient. Another technology we looked into was a flexible method for smart grid communication network capacity planning. Now, this ultimately addresses a problem that utilities and companies will be dealing with in the future, which is with all the smart grid technology and smart grid communication technology, we need to have more bandwidth available to make sure that we can, transmit all this data, right? Because we have so much data coming from each substation, each power plant, each distribution sub, each transmission sub. Wherever there is a node, there is probably some communication happening. So this paper identifies a method of planning network capacity so that we're always taking steps to increase the network capacity and ensure that we have enough bandwidth so that for the communication systems to work properly. So the first step is the orange circle, and you can see that it starts out by identifying major communication applications. So you can do this over a different number of periods. You can do this over a 2-year, study, a 3-year study, a 5-year study, a 10-year study. And you can identify major communication applications that will come over a certain period of time. Once you have that, once you have those specific applications, you can start to dive deeper into each application and measure specific communication aspects or characteristics of that type of communication. And that would include traffic patterns, which means, when the communication happens, during a day or during a month, you can talk about you have to account for message data size, or for a certain application, how big are the packets that you have to use to send the data, and the specific communication protocols. You can use all of these characteristics to approximate to create data profiles and approximate how much data each application is going to use. And then you can use all of these data profiles to approximate traffic on the communication network using average day or normal day ranges, and also stormy day or more heavy communication days. So in this planning method, they use two ideologies or philosophies. One is for just a normal day of normal communication. That could just be the average. And then the one is for extreme or a maximum strain on the network capacity. And but with this modeling is actually an iterative method. So once you approximate, your data profiles and you estimate the daily traffic, you can compare it to the actual traffic and then see, if how you can improve the system by, making your data profiles more accurate or identifying more applications that you didn't identify in the first place. The last technology that we want to talk about is communication and is coverage enhancement for communication systems using binary coding. So in this paper, we learned that using binary coding with a specific binary code book, I think that provided by IEEE, they were able to make the accuracy of the system and uh, the coverage of the system increase by using the binary code book and binary coding and using binary to encode the messages as they transmit and receive messages. So the result was that for any number of data packets, using the binary coding actually uh, took encoded the packets in less data. It transmitted it at the same rate, so that the rate of transfer was the same, and it was a higher recovery accuracy. So it was a higher the communication was not there was less there was it was able to resist interference and maintain uh, the integral part of the message and increase coverage. Now we're going to move into talking about some active companies and products that have to do with the technologies that we covered. So General Electric, as always, is always one step ahead of people, and they have a system that resembles the application of a wide area frequency monitoring network. This is called, uh, they call it WAMS, or Wide Area Management System. Um, which is really software and it's a software and hardware link. So they use a software called PhaserPoint, which is a real-time synchrophaser-based measurement and monitoring tool that is able to collect real-time data from the PMUs in the field. So they have phasor measurement units out in the field that are collecting the voltage and frequency of the system at real time, and they're transmitting it to the software. I think either over the internet or using some sort of probably encoded communication scheme to contact those measurements to a real-time system software that can be controlled by an engineer or by some sort of operator. Um, they can read these measurements and make adjustments as necessary. Right? So a few applications that can be used to operate the system more efficiently using this technology are active and reactive power monitoring, rate of change, frequency monitoring, voltage magnitude and angle difference monitoring, islanding, resync, and black start for distributed generation.
So another company is SNC Electric Company, and is currently using layered network approach to communication solutions, which allows them to deploy networks to meet the near-term requirements of customers looking to prioritize and transport data for mission-critical applications like like for fault location, isolation, service restoration, support secure and reliable data management with SCADA, create efficient operation with AMI backhaul, perform video surveillance, and support workforce mobility. So next slide is about Siemens. Um, Siemens Network Communication Technologies provides reliable connectivity between the installed assets and the control centers, and about how they ensure a fast and reliable feeder automation They're also using FDIR, which stands for fault detection, isolation, and restoration. So it detects fault segment in a distribution line, then isolates the fault by performing topology changes in the distribution grid, and finally restoring the initial topology once it is confirmed that the fault condition has been eliminated. So cybersecurity is the most important and also the most challenging part for the smart grid communication, since there's a large amount of data is transmitted through the communication system. This data can be cyber attacked by hackers or terrorists. The communication system becomes more vulnerable when it is not fully dedicated to the smart grid communication and shared with other users. So we have two levels of protections. At the physical level, the smart meters and LDCs have to be physically secured to prevent unauthorized access. At the software level, new advanced encryption algorithms have to be developed and applied. There are also some protocols that the smart grid needs to follow, which are secured socket layer and transport layer security to secure the system.
So lastly, we want to just talk about we want to talk about some important just the overall picture of the smart grid and the smart grid communication in this and in the smart grid. So ultimately, the smart grid will be optimized with smart grid communication because all of the independent parts of the system that currently aren't communicating will be able to benefit from one another because we will have the information that we don't have currently. So for example, generation will be able to talk to the power market, which will be able to talk to the DERs so that they know how much energy they need to provide, and they know how much energy the DERs are providing, and they know how much the costs are for generation that are changing in real time. Right now they have certain capabilities that allow them to communicate, but not in real time, and they aren't the measurements out from the field. So ultimately, the smart grid communication will play a very uh, effective role in smart grids. It will allow them to have self-monitoring capabilities, remote control capabilities, advanced data storage and analysis capabilities, and real-time, remote, instantaneous, accurate, secure communication on several levels. And the benefits of smart grid communication are several, but I've listed some here. Ultimately, it will allow for optimization in every domain, generate a more efficient generation load management, energy balance, smart power communication, smart network capacity planning, improved reliability and resilience, efficient energy and market operation, and even some sort of situational awareness. And yeah, that concludes our presentation. We just have some sources to the papers that we used and to the websites that we consulted. Thank you very much for listening.